And the flow control protocols we looked at were stop and wait and sliding window. So two main mechanisms for flow control. Stop and wait, simple but inefficient in that we send one frame at a time. Sliding window improves upon the efficiency by sending multiple frames before having to wait for an ACK, an acknowledgement. But is more complex. We're going to see that the error control mechanisms, the ones that we'll look at, are based upon stop and wait and sliding window. That is, we'll see they're very similar, but they add error control. Well, what is error control? Well, the ability to detect and preferably correct errors. Errors when something goes wrong across our link. We send some data and it either doesn't arrive at the destination. I send a data frame from source to destination, but there's an error on the link such that that data frame doesn't arrive at the destination. It's lost. We say that's a lost frame. No frames received, but I send something. That's an error. Because we know that in many applications, when we send data, we want to make sure that it's delivered 100% reliably to the destination. Everything we send arrives. Why may data be lost? Well, it may be a characteristic of the link. Not all links and the physical layer protocols we use are not perfect. So we may send some bits and it may be that the receiver cannot receive a signal that represents those bits. That's common in wireless systems. I transmit a data frame from my laptop to the access point, but there's some interference when I transmit it such that the access point doesn't receive or cannot make out that it's received any bits or a frame. So we can talk about frames that don't arrive at the destination. In fact, when we have a link which is made up of repeaters and intermediate components, it may be possible that there's an error on one of those intermediate devices such that, for example, they fail such that the frame doesn't get to the endpoint. So we may have lost frames. The other thing may happen is that a frame arrives at the destination, but that frame has some bits in error. Our frame may, say, have 1,000 bytes of data. We receive that frame, and the receiver can detect that that frame of those 1,000 bytes, maybe several bytes are wrong. Bit errors. Send a bit 0, receive, and think it's a bit 1. We call that a damaged frame. We receive the frame, but we can detect that it's wrong. And we need to fix that case as well. So the techniques we have available, well, really we can break them into two different types of techniques to detect and, importantly, correct errors. There's what's called error detection and FEC, forward error correction. Discussed in previous topic. Well, no, we didn't. We skipped that topic. Okay, that's one technique for correcting errors. The idea, and we're not going to cover it, the idea is that when we send data, we actually send either some extra information or in fact transform that data that we send into something different such that if there's an error at the receiver can detect that and even correct it based upon the extra information sent from the source. We're not going to try and discuss that. If you want to look and find out how error detection works, possibly you've seen it in other courses looking at parity checks in computer hardware, one form of error detection. CRC16, CRC32 is another error detection algorithm. And there are different forward error correction algorithms. If you want to see some examples, on the course website you can find the lecture notes for that topic. We're not covering it this semester. We're going to cover the other approach, which is maybe is probably the most used approach. And that is that we send our data And if our receiver doesn't receive that data, then we ask the sender to send again, retransmit. And it has different components, or different ways to do it. One is called a positive acknowledgement. Source sends data to destination. If destination receives that data, it sends back an ARQ, a positive acknowledgement saying, thank you, I received that data. So send data, the normal operation, the source sends data to the destination sends back an ARQ, an acknowledgement, indicating to the source that it's received, that the destination's received the data, that we didn't lose data, that it wasn't a damaged frame. But what if it is? What if the frame is damaged, or what if the data doesn't arrive? Well, if in the normal operation we send data and expect an ARQ back, if we don't receive an ARQ after some time period, the source will retransmit. So the idea is, from the source's perspective, send some data, expect an ARQ to come back within some time period. If you don't receive that ARQ, then send the data again, and that's a retransmission. So we use positive acknowledgements, and we use retransmissions after timeouts. A timeout is some predefined period that the source will wait before retransmitting a data frame. There's another mechanism that's sometimes used called a negative acknowledgement. A positive acknowledgement is saying, is the destination saying, data was received successfully, positive. A negative acknowledgement is the destination saying there was an error. Either the data wasn't received or the data was received in error, which is a negative result. And there should be a similar response from the source, retransmit, send again. So we'll see some examples of these mechanisms when we go through different error control protocols. So, error control, fix errors across our link. If something goes wrong, we want to make sure that the data eventually gets delivered to the destination. And the approach we're looking at is using retransmissions. Send the data, if it doesn't get there, send it again. And if it doesn't get there the second time, send again, with the hope that after trying several times, it'll eventually get there. Now, there's some special cases to consider. What if we try too many times? We'll talk about that as we go through. Using acknowledgements and retransmissions and timeouts. Together, acknowledgements, retransmissions, timeouts, both positive and negative ARQs, those mechanisms we classify and call automatic repeat request. So we have requests coming back and we aim to automatically repeat the data when needed. And that's abbreviated, or the acronym is ARQ. So we generally talk about ARQ mechanisms. And the three versions of ARQ mechanisms that we'll go through, the three main ones, are stop and wait ARQ, go back N, and selective reject. And what we'll see is that stop and wait ARQ is very similar to stop and wait flow control. Send one data frame, get one ARQ back. Data, ARQ, data, ARQ. And the next two, go back N and selective reject, use the concepts of sliding window flow control. We have a window. Send a window of data frames, get some ARQs back. Send a window of data frames. But they have extensions upon the flow control mechanisms to indicate if an error has occurred. And that's what we need to go through. Let's start with stop and wait. Very similar to stop and wait flow control. The rules: the source sends a single data frame, and then it starts a timer. Okay, you can think the source has a timer. We send the data frame, start a timer, and as with stop and wait flow control, when we send the data frame, we must wait for the ACK to come back. After sending that data frame, we store a copy of that data frame in the buffer at the source. We just maintain a copy. We're waiting for the ACK to come back. If the ACK arrives back within some period of time, we'll stop the timer and move on to the next frame. This is a positive ACK scheme. Send the data. If we receive an ACK back, that means that data was successfully received. So the normal case, if there are no errors, data, ACK, data, ACK. But what if there's an error? What if I send the data across the link, but for some reason it doesn't arrive at the destination? Well, if the data doesn't arrive at the destination, then the destination is not going to send an ACK back. So from the source's perspective, it sends the data frame and now waits for the ACK. It's not going to wait forever. The ACK is not going to arrive because the data was lost. So the source, when the timer reaches some predefined value, we say when the timer expires or a timeout occurs, the source assumes that means the data was lost and retransmits a copy of the data that it previously sent. Sends it again. There are a few more mechanisms that we'll go through, but let's illustrate that with a diagram. And I think it's almost the same diagram that we've seen with stop and wait flow control. I've made up a scenario where A has three chunks of data to send to B. And as with stop and wait flow control, we create a data frame, send it to B. If it arrives, B processes that data, delivers it to the layer above, and sends back an ACK, a positive ACK, saying thank you, that was successful. So we get a data and an ACK. And A, because of the flow control mechanism, could not send the second piece of data until it received the ACK. It receives the ACK, sends the second data frame. So this is data frame 2, or the frame containing data chunk 2. Sends that, B receives, processes, sends back an ACK saying thank you. Data 3, ACK, and we can keep going. This is for the simple case where there's no losses, no errors. In fact, it looks just like stop and wait flow control. The first thing to notice, if you compared it to the stop and wait flow control protocol, with stop and wait ARQ, we include sequence numbers. Our data has a sequence number. We saw with sliding window we needed a sequence number, like 0 through to 3, 0 through to 7. But with stop and wait flow control, we didn't have a sequence number. It wasn't needed. But we do need it here. In fact, we need a 1-bit sequence number. With 1 bit, the sequence numbers in decimal are 0, 1, 0, 1, 0, 1, just alternates, sometimes called alternating bit protocol. So we see that the first data frame has sequence number 0. I've drawn it in the brackets here. The second data frame has sequence number 1. The third data frame, a new one, has sequence number 0. We'd see it would be 0, 1, 0, 1, 0, 1, just alternates because we just have a 1-bit sequence number. So that's a small difference to stop and wait flow control. The ACKs have what we call an acknowledgement number. And it works similar to the ACKs in sliding window and the ACK numbers in most protocols. The ACK number, the acknowledgement number, indicates the next sequence number of data expected. Send data with sequence number 0. B receives that, successful, sends back an ACK with ACK number 1, with the meaning of, I've received data 0, I now expect data 1. Data with sequence number 1. A sends data with sequence number 1. B receives it, sends back an ACK saying, thank you, I've received that data. I now expect data with sequence number 0. So the ACK number here is 0. So the next one we send is data with sequence number 0. Note that, and this is what some people get confused or miss, the ACK numbers, in fact I think all of the protocols that we look at, the ACK numbers indicate the next value expected, not the last value received. I now expect 1, so A sends 1. I now expect 0, A sends 0. Okay, just make note of that. That was the same in sliding window. Alright, you're not very interested in this because there are no errors. The reason for stop and wait ARQ is to handle errors. What if something goes wrong? Let's consider a case. Try and draw. What happens if, let's say, the second data frame, this one, doesn't arrive at B? I'll give you a few minutes to try and draw this diagram with stop and wait ARQ, but consider the case that the first one's okay, but the second data frame is lost between A and B. It doesn't arrive at B. What happens? Try and draw that diagram. Frame loss here. We lose data. So the first data frame is successful, so it will look exactly like the first frame here, but the second one doesn't get to B. Then what happens? And I'll try and draw it as you are as well. What happens next? So this is the same. I've just simplified it a little bit. I haven't written data or ACK, but the sequence numbers of our data, our ACK. What happens if this one doesn't arrive at the destination? It's going to wait, the source is going to wait for its timer to expire. So how do we draw that? Well, we're going to say it's sent, and let's say it doesn't arrive. I'll draw a cross, meaning that frame that was sent doesn't get to be the destination. What happens next? Well, note that whenever we send a data frame, we start a timer. So you think we start our stopwatch. And we're counting and waiting for an ARQ. The source is waiting for an ARQ to come back. Of course, there's never going to be an ARQ, because B never receives the data, and therefore B will never send an ARQ. So A, the source, has a timer, and once it reaches some value, some predefined value, we say that timer expires, or a timeout occurs, and that triggers a retransmission. So I'll say that we have some timer, say it starts at some point, and let's bring it down to here. That's indicating some timer or some timeout period. And what happens is, the idea is that we transmit our data frame. Now we wait for an ARQ. We're waiting, we're waiting. We expect to receive that ARQ within some reasonable period of time. And in fact, we'll talk later of how we determine this time. But we expect to receive the ARQ. We haven't received the ARQ. We haven't received the ARQ. All right, we've waited long enough. That's this timer expires. We've waited long enough. We assume that something's gone wrong. The data was probably lost. Maybe the ARQ was lost in response. So we assume that an error has occurred. And what we do to fix this error is to send our data again. We retransmit. So we'd send the same data frame a second time. And the sequence number of that data frame is 1 again. It's the same data frame. It contains the same piece of data. So the first data frame contains sequence number 0. We got an ARQ back saying, I now expect 1. Everything's okay. We send the second data frame with sequence number 1. Doesn't get to B. A doesn't know what's happened here. Remember, these are two computers at the end point of the link. We're waiting for an ARQ. We're waited too long. Our timer expires, or a timeout occurs. Means, let's try again. Retransmit that same data frame, same sequence number, and send it again. And let's assume, for simplicity, that it arrives this time. So keep drawing the diagram and assume that the retransmitted frame arrives at B. What happens next? Let's say it arrives. And it arrives successfully this time, so the source simply sends back the ARQ. And let's keep it simple and say the ARQ arrives back. And that allows the source to send the next data frame. And we can keep going. Let's make note of our numbers. If B receives a data frame with sequence number 1, the ARQ that comes back has sequence number what? 0, because we only have a 1-bit sequence number. We're just going to alternate 0, 1, 0, 1, 0, 1. And the ARQ is the next number expected. So the next data frame will have sequence number 0. And I will not draw the ARQ. We'll have another ARQ back, and so on. Okay. So that's just the case where one of the data frames was lost. It didn't arrive at the destination. It also covers a case where the data arrives at the destination but is in error. That is, I receive some frame, I look at the bits at the destination, and I detect that there are a lot of errors in those bits. Something was corrupted along the way. In that case as well, the destination may not send back an ARQ. If the data is received in error, it's treated the same as if the data wasn't received at all. Don't send an ARQ, and eventually the source A would retransmit. There are some variations on that we'll see later. But in this case, send the data, doesn't arrive, wait for a timeout to occur or a timer to expire, retransmit. Any questions on stop and wait so far?
In the instance that the data is received successfully, the ARQ does not arrive.
That's our next case, okay? We'll come to that. That's good. So the question is, what if... So this was a case where the data didn't arrive at the destination. What if, for example, the data arrives, but the ARQ on the way back is lost? Let's try, or you try, see what happens. So on the next slide, so we just covered the case of lost data. We lost one data frame. Now try and draw a diagram is if the data arrives, but the ARQ doesn't get back to the source. A lost ARQ. So this was the case of a lost data frame. The second data frame was lost. Consider the case where maybe the second data frame, or it doesn't matter which one, say even the first data frame is received, but the first ARQ doesn't make it back. Anyone have an answer? Let's say the first acknowledgement sent by B doesn't arrive back at A. Try and draw that diagram. Need a piece of paper, pencil maybe. Your pictures don't have to be as nice as mine, but try and capture the main exchange of frames and the events that occur. So the ARQ is sent but doesn't get back to the source A. Let's try and start drawing it. what happens next?
I think the timer expires on the data and retransmits.
Again.
I think the timer expires on the
Yep.
data.
All right. So same as before. From the source's perspective, we've sent data. We start our timer. So we're waiting for an ARQ. We're waiting for an ARQ. And eventually our time is going to expire because we're never going to receive the ARQ. The source doesn't know whether the data frame was lost going to B or the ARQ frame was lost coming from B. It doesn't know. It just knows if its timer expires, something went wrong. And when something goes wrong, we resend the data. We retransmit. So yes, a timer expires and then resend the data. Now let's add some more information to this diagram, which I didn't show in the last picture, but let's go back. Sorry. To see why we got sequence numbers, we'll eventually arrive at that. Note that, so this is the case, no errors, normal behavior. Send the first data frame. We had 3 chunks of data. First data frame contains the first piece of data. It was delivered to the application or the user at computer B. Let's say, what is the data? From the protocol's perspective, the data can be anything, just a sequence of bits. But let's say data 1, this protocol is used between 2 banks. Okay, a link between 2 banks or 2 branches of a bank. And the data is some messages about an account transaction. For example, data 1, you don't have to write this down, just to give you an idea of what's going to happen. Let's say data 1 is I don't know, increase Steve's account by 10,000 baht. Okay, so it's some message from some 2 computers in a bank indicating what to do with an account. So increase my bank account by 10,000 baht because I deposited money in an ATM, for example. So it sends to the central server saying increase that. So that's data 1. Data 2, data 3 may be other messages like increase by 5,000. We won't get to them in a moment. Well, let's write them down. They are different messages. Data 2 is something else like decrease. Maybe I withdrew some money after I deposited. Decrease by 2,000 baht. And data 3 is something else. Decreased by 1,000. Just made up examples of data. In fact, the data may not be messages like this, it can be anything. But we'll see why it's important to consider what happens with errors. So in the first case, the computer sending these messages to, say, some central bank server that records my account total. Data 1 is delivered, and when the data is delivered, let's say the application there, or the database that stores all this information, updates my account balance from originally my balance was 0 baht. After receiving the first message, my account balance would go up to 10,000 baht. After receiving the second message, at this point in time, the application here would increase my account would decrease my account balance down to 8,000. And then after receiving the third message, it would be down to 7,000. Okay, that's the normal operation. Because on one computer, it's sending some messages to the central database that keeps my account balance, and they were the 3 pieces of data. Although it didn't draw it on the previous, let's hide this one. On this case, does it work? That is, if we're using this protocol to communicate between the devices, does the application still work in the same way? Let's see what happens. The first data message was received here. Sorry. So data 1 was received at this point in time, and that would increase my account to 10,000. Data 2, from the receiver's or the server's perspective, was not received until this point in time. The second message is received. Of course, that would take my account balance from 10,000 down to 8,000. And then the third message, and I don't think I drew it, but I think you can work it out. The third message, okay, here it is, arrives here. And that decreases my account balance down to down to 7,000. That is, even though we lost some data, even though we lost this message between A and B, those three pieces of data, data 1, 2, and 3, were all delivered to B in order. So we get the same behavior as if we'd lost no data. So that's the intended behavior. That's good. Now let's see what happens with the next case where we lose the ARQ. Data 1 arrives here. That is, at this point in time, B receives the first data message, increases my account by 10,000, so my balance is now 10,000 baht. The ARQ was sent back. B received it, received the data, increased my account balance, sent back an ARQ saying thank you, but there was an error. The ARQ didn't arrive. And like we discovered, again, what the source is going to do is going to time out. It's not going to receive the ARQ, so it's going to, eventually its timer will expire and trigger a retransmission. So we're going to retransmit. I'm sure you've finished the diagram to see what happens after some time period. Just draw it to here. That's our timeout period. At that point in time, we realize we haven't received the ARQ, so let's resend. And we send the original data again. And that's going to arrive, assuming there's no problems from now on, and eventually we'll send back the ARQ. Assuming there's no more losses along the way. And I'll just keep. Now, what happens next? From the destination's perspective, B received the first data frame at this point in time. Frame 1, increased my account balance to 10,000. Because of the ARQ was lost, A retransmits that same piece of data. B receives the same piece of data, message 1 again. The data is increased Steve's account by 10,000 baht. What happens? Nothing. Well, that's what should happen. If B receives this data and processes the data, we'll have a problem. Because what was sent was increased by 10,000, decreased by 2, decreased by 1. So the final balance should be 7,000. But if, because of the protocol we retransmit, because of the lost ARQ, if B processes this data and increases my account by another 10,000, we're going to have a problem. We haven't achieved what the intended data transfer was built for. So in this case, what B does is ignores this piece of data. So in the case where an ARQ is lost and A retransmits, even though B has received the data before, it receives it the second time. Same data. In this case, B must ignore this data, discard the data. So it receives it, looks at it, detects that it's the same as the previous one I received, and throws it away. Because if it didn't discard the data, my account balance would now be 20,000 baht, which is incorrect. So in this case, it's important to note B receives the data but discards it. It ignores the contents. Any questions? There should be one question, at least. How does B know? How does B know that this data is a retransmission of this data? It may have been that there were two messages. Data 1 was increased my account by 10,000, and data 2 was a distinct, different message, but in fact also said increased by 10,000. Maybe that's the intended operation, increased by 10 plus 10 to 20,000. How does B know that this data message received is in fact a retransmission of the first one received? It's the sequence number. And if we go back and draw those sequence numbers, you'll see that. A sent data with sequence number 0. B sends back an ARQ saying the next number I expect is 1. A doesn't receive that. Times out and retransmits the original one, which used the same sequence number, 0. B receives this frame. B was expecting sequence number 1, but received data with sequence number 0. It's unexpected. Therefore, B knows to ignore this. It must be a retransmission of some previous piece of data I received. So B ignores the data, but still sends back an ARQ with ARQ number. What ARQ number here? Here's an ARQ. What number does B send back in it? You've got two guesses, 0 or 1. Left hand up for 0. Right hand for 1. It's 1. It's your right hand. It's the next number expected from A. We still expect 1. We just received 0, okay, sent back ARQ saying I expect to receive 1. I just received 0 again. Oh, that's a retransmission. Throw it away, discard, but still send back an ARQ saying I'm still waiting for sequence number 1. And hopefully the next one that comes will be 1, and we can keep going assuming no data loss. The second data frame delivered and processed, and the third one. This is why we include or need sequence numbers in stop and wait, so that B, in this case of a lost ARQ, can distinguish this frame is just a copy or a retransmission of the previous one. Discard. If I could not distinguish, and if I processed this retransmission, I would have increased my account to 20,000 minus the 3,000 at the end. I would have made 10,000 baht, which was wrong. So the case of a lost acknowledgement. Of course, our data doesn't have to be financial data, it can be anything. It can be part of an image, a file, but the same thing applies. That we need to detect retransmissions and discard them where necessary, so that the final data received at the application or by the user here is in fact an exact same copy as what was at the user at the source. So we've got 3 examples. The normal case, that's easy. We have sequence numbers, and we've looked at a case with lost data and a lost ARQ. Just going back to our description. Alright, this is our description of the protocol. Source transmits a single frame, starts the timer, stores a copy of that frame. If we receive the ARQ before the timer expires, fine, move on to the next frame. If the timer expires before receiving the ARQ, then retransmit that copy. In practice, we have a limitation on the number of retransmissions. Let's say I send data, it doesn't arrive, it's lost, so I retransmit. And that doesn't arrive and it's lost, so I retransmit again and again and again. Well, I don't go forever. I must eventually stop retransmitting and accept the fact that my data is never going to get there. And maybe present an error to the user saying, I could not send the data. So we have a limit on the number of retransmissions. We have frames with a 1-bit sequence number. We need this 1-bit sequence number, this 0-1, alternating, for that special case of if we receive a retransmitted data segment because of a lost ARQ, the destination can detect that and discard that. That's the purpose of the sequence numbers. Simple, but the same as stop and wait flow control can be inefficient. We still have this issue of send some data, wait a long time before we can send the next piece of data. So the same inefficiencies of stop and wait flow control. Before we look at using the sliding window mechanism to improve the efficiency, any questions on stop and wait ARQ? Now's the time to ask. People looking through the lecture notes, good. Next scheme we'll go through is called Go Back N, and it's based upon the sliding window mechanism where we can send W frames before we have to wait for an ARQ. But we also have a retransmission scheme. So think we have the sliding window flow control, but also, as in the sliding window, if there's no errors, then it behaves just like the sliding window mechanism. So we send our data and ARQs come back. So if the destination receives the data, it sends back an ARQ containing the sequence number of the next expected frame. That's what we've seen all along. In practice, it may not be an ARQ for every data frame received. It may be every second or after every time period. Now, what if an error is detected? That is, destination detects something's gone wrong. Then it can reply with a negative ARQ saying, I've detected something's gone wrong, please resend. or please fix it. So in stop and wait, we had a positive ARQ. We send our data, we receive an ARQ indicating it was successful. We have a positive ARQ in sliding window if there's no error, but we also have a negative ARQ saying destination has detected something's gone wrong, therefore it requests the source to fix that. Negative ARQ, a NAQ, or sometimes a reject message, rejection message. Now, what does the source do to fix the problem? When the source receives this negative ARQ telling it something's gone wrong, it in fact contains an ARQ number saying the next number expected by the destination, and that triggers the source to retransmit. And we'll see, importantly, compared to our third approach, that the source will need to retransmit, here. The transmitter, the source, must go back and retransmit all the frames since that lost frame. And that's where the go back n name comes from. We go back and retransmit n frames, not just one frame. There are a few other features, but let's go to the example. This is a diagram slightly different from what we've drawn. It just hides the details of the frame transmission. So it just shows frame 0, frame 1, and so on. Because there are many frames, to keep it condensed. A has many frames to send to B. In this example, we have a window of 7 frames. So we see our sequence number, you'll eventually notice, goes from 0 up until 7 and then wraps back to 0. So frame 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, and so on. So in this example, we still have sequence numbers as in sliding window. In this one, it goes from 0 to 7, a 3-bit sequence number. The first 4 frames arrive at B successfully. Frame 0, 1, 2, and 3, they all arrive at B. And in this example, B is sending an ARQ for every second frame. So it could have been an ARQ for every frame, but I think just to keep the diagram simple, we're drawing an ARQ for every second frame here. Receive frame 0. Receive frame 1, send back an ARQ, and another name we saw was this request, what do we call it? Request reply, indicating the next number expected. Frame 0's arrived at B, frame 1's arrived at B, we now expect frame 2. So we see RR2, an acknowledgement, positive ARQ, saying I now expect 2. Frame 2 arrives at B, frame 3 arrives at B, we send back an ARQ saying I now expect 4. Nothing's gone wrong at this moment. Everything's okay. Frame 4 was transmitted by A. Remember, A has a window of frames it's allowed to send. As in sliding window, we're allowed to send many frames before waiting for an ARQ. A has sent frame 3, 4, 5, 6. Frame 4 is lost. It doesn't arrive at B. So let's say we have bad luck at this point and we lose frame 4. Doesn't arrive at B. Frame 5 is not lost. It does arrive at B. The arrival of frame 5 at B tells B that something's gone wrong. Because from B's perspective, it's received frames 0, 1, 2, 3, and then 5. B expects to receive the frames in order. That's how we use our sequence numbers. We've received a frame out of order. We've received 5 before we receive 4. That tells us something's gone wrong. 4 has been lost in this case. So that triggers B to send this negative ARQ or reject message back to A saying something's gone wrong. I still expect frame with sequence number 4. So you see a reject 4 message here. And that frame 5 that was received by B is discarded. It's thrown away. It's not stored in memory. We throw it away. Even though we successfully received it, from B's perspective, it must receive the data in order. If it's received 0, 1, 2, and 3, the next one it's going to accept is 4. If it receives 5, throw it away. 6, discard. It's just a simple procedure for the receiver. If you don't receive a frame in order, discard that frame. When A receives the reject message, that tells A that it needs to retransmit frame 4. A has sent frame 4, but then it receives a reject message with the ARQ number 4 telling A something's gone wrong. Most likely frame 4 has been lost, therefore we need to retransmit frame 4. But we also need to retransmit the frames we've sent since frame 4. So A has sent 0 through to 3, 4, 5 and 6. B tells us frame 4 you need to send again. In go back N, in fact A needs to go back and retransmit 4, 5 and 6. So those all 3 frames, and we see that here 4, 5 and 6 are retransmitted. This places this makes it easier for the destination in that when the destination receives a frame out of order, it simply discards it. It doesn't need to store it in memory. It uses less memory at the receiver. But as we'll see compared to the next approach, it introduces extra retransmissions, which is bad for efficiency. Because, in fact, we'd sent 4, 5 and 6. 5 and 6 were received. Only 4 was lost. But with this scheme, we need to retransmit 4, 5 and 6. That is, the lost frame plus any sent after the lost frame, but before receiving the reject. And in this case, so far, 4, 5 and 6 arrive successfully. So we get an ARQ back saying here we receive 4, 5 is expected, B receives 5 and 6, 7 is expected. Let's stop there. Questions?
So when you calculate efficiency for this method, would retransmissions be null?
When we calculate efficiency and also throughput, think of throughput is the rate at which we receive the real data, original data. So what real data has been received? All right, frame 0, or the data inside frame 0, 1, 2, 3, 4 was not received at this point. Even though 5 and 6 were received by the B, they were discarded. So we do not count them as real data being received. It's only until at this point we receive 4, 5 and 6, the retransmitted values, do we count that data as efficiency. So in fact, this is somewhat inefficient in that frames 5 and 6 arrived but were discarded, and we actually had to resend them, wasting some time. But that makes it, the reason for doing that is to simplify what B, the destination, has to do. It just receives frames in order. We'll go through the last part in a moment. That's an extra feature. Any other questions? So we use a sliding window. We use a negative acknowledgement telling the source that something's gone wrong. And that is sent when the destination recognizes a frame has been lost because it receives one frame out of order. expecting 4, receive 5, tell A to resend 4. And resend 4 and all subsequent frames that you've sent. In this example, 4, 5, and 6. Let's, for now, skip the last part and look at an alternative called selective reject. Very similar, except if we see the same scenario, 4 was lost, 5 has arrived, 6 arrives. Compared to go back N, what B does is those 2 frames received out of order, frame 5 and 6, it stores in its buffer. Sends back a reject message or a selective reject. Really, you think that means B is telling A, please retransmit frame 4. And in selective reject, we only need to retransmit that 1 frame. So we see A sends 0, 1, 2, 3, successful, 4, 5, and 6. B does not receive 4, receives 5 instead. Sends back this negative ACK saying, please resend 4. Here. It stores 5 and 6 for future use. A receives the selective reject message and retransmits 4. And then moves on to the next frame after 6, so 7, 0, 1. If we compare between so far go back N and selective reject, just in the first portion, in go back N we need to go back and retransmit all frames since the lost frame. 4, 5, and 6 in this example. That is easy for the receiver because it doesn't have to store frames received out of order, but it's inefficient because we retransmitted 2 frames which are actually delivered. Whereas with selective reject, we only need to retransmit 1 frame. We don't need to retransmit 5 and 6 because 5 and 6 are buffered by the receiver. So selective reject is is more complex for the receiver, requires more memory and more processing to put frames back into order, but is more efficient because we only need to retransmit 1 frame. Go back N is less efficient but simpler than selective reject. Selective reject requires extra memory, more complex at the receiver, but can be more efficient than go back N. So they're very similar, those two, just for that, the way that the retransmission occurs. Yep.
Does the receiver side jitter in the selective reject have an impact on the efficiency on
So the variation in the delay and the selective reject, in fact, it can get quite complex, especially when we have things like losing 2 frames. And the selective reject normally indicates, okay, we're saying this indicates 1 frame to be retransmitted. If we lost 2 frames in this case, what happens? Or what if the delay between frames varies significantly? That has an impact on the efficiency, and we're not going to discuss and analyze in that level of detail. We'll just say, comparing the 2 approaches, selective reject in most cases will be more efficient than go back in the most typical cases. In some cases it may not be, or it may be equivalent. What did we miss? Almost done. The extra features down the bottom of the diagram is that we still have a timeout mechanism. So far, we've seen with go back N and selective reject, we retransmit when we receive a negative ACK. because the destination recognizes something went wrong because the frames arrived out of order. But as with stop and wait, ARQs can be lost. We send frames, the ARQ is sent back, but it doesn't get back to A. If we don't receive the ARQ in time, we may have a timeout that says, okay, let's do something about it. And what do? There's a special message which requests a reply, or requests an ARQ from B. That's this special message here saying, we're waiting for an ARQ, we're waiting for an ARQ, we don't receive an ARQ because it was lost. Let's request an ARQ from B. Hopefully it won't be lost this time. The ARQ comes back, and that tells us that we can move on to the next frames. So there's this extra feature to request an ARQ from the destination. An ARQ request, or this RR message with some special bits to indicate it's a request. The same applies in selective reject. They're the same from that feature's perspective. Try and pick up the main points between the difference of these three ARQ mechanisms. Stop and wait ARQ, almost the same as stop and wait flow control, but we now have retransmissions. And the basic scheme is, if we don't receive an ARQ within some time period, retransmit. With go back N and selective reject, we use sliding window. We're allowed to send W frames, or a window size of frames. We detect errors, or we detect lost data at the receiver when it receives frames out of order. Because if we send 7 frames and we receive all but one of them, then we detect which one's missing and ask the sender, or ask the source to send again. Go back and selective reject are based upon sliding window. Go back N, and to finish here. Sorry. Selective reject compared to go back N minimizes retransmissions, which is a good thing compared to go back N. But it requires the destination to maintain some buffer to receive frames out of order, which requires also more complexity to put them back into order. So they are the disadvantages of selective reject compared to go back N. Turns out that go back N is more widely used. Even though it's less efficient, the simplicity makes it an appropriate trade-off. Selective reject is used in some cases, say when efficiency is very important in this case. All three of those ARQ schemes are used in protocols and in systems today, or variations upon them. Last 10 minutes, finish this topic. We've skipped one slide. We need to go back to it, but before we do, all of these schemes, these ARQ schemes, especially stop and wait, need some timeout period. We send our data, we wait for the ARQ to come back. How long should the timeout period be? If I ask you a question in the lecture, how long should I wait for you to reply? If I wait forever, we will not communicate much in this lecture. You will not learn much, because I'll ask you a question at the start and I'll stand here for 1.5 hours. How long do I wait before I, for example, retransmit that question? Maybe you didn't understand, maybe you didn't hear me, so I ask again the question. Well, this is the timeout period. I send some information to you. If that information is lost along the way, then I should retransmit. So how long do I wait before I retransmit? That's an important thing. Now, what if I say, what is your name? 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 In that case, I'm asking a question, I'm sending data, I'm waiting for a response, but I only waited a very small amount of time before I resent. I sent the message, I did wait for a response, but I didn't receive a response within half a second, so I resent the message. It was very inefficient because he was trying to think of his name, he knows it, he would have said. He was sending me his name, but I didn't wait for it to arrive. So we need a trade-off. We need a timeout period which is long enough to give the receiver a chance to reply, but is not too long such that the source waits a long time before retransmitting if there is an error. Okay, so we need to choose a timeout that deals with this trade-off. How long should it be? Well, as we said, long enough to get an ACK back if there's no loss of data. Well, how long does it take to get an ACK back? It depends upon many factors. It depends upon our link, our data rate, our propagation delay, processing. It may in fact vary. So it's actually, although we can, propagation time may be variable, processing may be variable, it's hard to estimate how long it takes to get an ACK back. So with real links, it's hard to know. So usually we need to set it quite large. So if we estimate the time to get a response back is 1 second, then, well, maybe we give it some freedom and set it at 1.5 seconds, because sometimes things vary. Now, we could set it at 10 seconds, so give us enough time to get a response back, but the problem there is if it's too long, then if we send our data and that data is lost, we're waiting for 10 seconds before we retransmit. We spend a lot of time waiting, wasting our resources, not sending. So too long wastes the source's time before it retransmits if data is lost. A timeout which is too short leads to many retransmissions, which are also wasteful of our network resources or our link resources. So, choosing a good timeout value is in many cases difficult. And usually protocols either define what the timeout value should be or have an algorithm for calculating or estimating what it should be based upon what's happened in the past, for example. Yep.
Layer 2, assuming it's Ethernet, will auto-negotiate as part of the protocol.
And so in some data link layers, like in your LAN, well, what does the time depend upon? Propagation time, data rate. Well, if you know those characteristics, then the device can calculate what it may be. If we know the distance, or if we can test what the propagation time is, then we can estimate the timeout period. Yeah. Yeah. So, but we need to know in advance, or we need to determine it in advance so that the source knows how long it needs to wait before it retransmits. In general, it's quite difficult to work out what is the optimal timeout period in practice, but it needs to be decided. That's one design issue with all of these protocols, retransmission protocols. The last few slides, you'll have a look, just some examples of some specific protocols that use these retransmission schemes. There are many. We need to jump back. One more slide. Where was it? Here. It applies to all of these schemes, both flow control and error control. We talk about sending frames of data. How big are the frames? Usually a protocol, a specific protocol, places a limit on the size of the frame, the upper size, upper limit. That is, for example, most LANs, Ethernet LANs, in the normal case say the frame size can contain no more than 1,500 bytes of data. So that's an example value. Means, so if I draw my frame, we may have a header and some data. We may have a trailer as well. A protocol or a standard would specify, well, how much data can we put in here? Usually there's an upper limit. It can be less. One example may be 1,500 bytes. Meaning we cannot put more into that one frame if we have. So if this is the maximum size of our frame, if the data to send, I have 3,000 bytes, then I would normally create 2 frames, split it into 1,500 each. If the data to send was 1,501 bytes, I would have 2 frames. One is 1,500 and the other one most likely 1 byte. Okay. If the data to send is 1,500, we'd have 1 frame. If it was 10 bytes, then we'd have 1 frame. So we usually have a limit on a maximum amount of data to put in the frame. What is the optimal value? What is a good value? Well, there's a trade-off. The larger the frames, the more efficient we are with respect to the overhead, the header. Think of this picture. If I drew it to scale, we have a header. Normally that's fixed in size. Let's say, let's give it a number, 20 bytes. Which means if we have a 1,500 bytes of data, we have an extra overhead of 20 bytes. So in this case, we'd send 2 frames, so we need to send 40 bytes of overhead. But if our frame size was increased to 3,000 bytes, in the first case when we have 3,000 bytes of data to send, we'd send just 1 frame. If we could fit it all into 1 frame, as opposed to 2 separate frames, we reduce the overhead. Because with 1 frame, we just have 1 header of 20 bytes. With 2 frames, we have 2 headers, totaling 40 bytes of overhead. So the larger the frame, the lower the overhead of the headers. So we want a large frame for that perspective. But there's some reasons for a small frame. Consider the middle point. If we send a large frame, let's say we have 3,000 bytes of data to send. If we send 1 large frame of 3,000 bytes and there's 1 error, then we need to retransmit that entire 3,000 bytes. But if we send 2 smaller frames and there was just 1 error, it means one of the frames would be received correctly. We only need to retransmit 1 of those 2 frames. We only need to retransmit 1,500 bytes. So generally, in the case of retransmissions, we'd like to retransmit just small frames. We don't have to resend so much. So we want smaller frames from that perspective. Another case may be the buffer size at the receiver. If we have a buffer of, it's a bit hard to illustrate, if we have a buffer of 4,000 bytes, if our frame size is 3,000 bytes, how many frames can we receive in the buffer? How many 3,000 byte frames can we receive in a 4,000 byte buffer? Just 1. Okay. What if our frame size was 1,000 bytes? How many can we receive? We'd receive 4. That is, with a large frame, we may be inefficient in filling up the buffer. With a 3,000 byte frame, we only use 3 out of the 4,000 bytes of the buffer. But with 4 1,000 byte frames, we could fill up the buffer. So in fact, Generally, we want to use smaller frames so we can be more efficient in using the memory at the receiver, the buffer at the receiver. There are some other reasons as well. So it's a trade-off. Large frames minimize the overhead due to headers. Small frames, for various reasons, make efficient use of buffers, reduce the overhead if we have to retransmit, and there's some other things like sharing amongst multiple users. In practice, usually the upper limit is determined by the protocol. Wired LANs, 1,500 bytes is the typical upper limit. You can have smaller, but that's usually an appropriate trade-off for that type of network. So there are two design issues. How big should our frames be? And what was the other one? How long should our timeout be? Okay, important design issues. Out of time, finished on this topic. Tomorrow I will not teach you. On Wednesday we'll cover the next topic of circuit and packet switching. We're going to skip multiplexing. We'll see you then.